Welcome back to Differential Calculus. In this video, I'm going to introduce you to the indefinite integral. We saw previously the idea of an antiderivative, a function whose derivative is the function in question. We saw through the fundamental theorem of calculus that the antiderivative is incredibly useful for dealing with integrals. But because it's not unique, it's hard to talk about antiderivatives as a general idea on their own. And for that, we introduce a new concept known as the indefinite integral. Let me get my head out of the way, and I will write down a little bit more of what I mean. An antiderivative is any one function, we generally denote using a capital F of x, such that capital F prime of x is equal to little f of x, right? So if we're given little f of x, we find a function capital F of x, so that if we differentiate capital F, we get back to lowercase f. The indefinite integral is the family or collection of all of the antiderivatives of little f of x. And that seems, at first glance, like an impressive claim. It feels like if there are infinitely many different antiderivatives for any function, well, any function that has antiderivatives, it feels like it should be difficult to actually figure those out. But it turns out to be fairly straightforward. I'm not going to get into the proof of this theorem, but we do have a nice theorem on that front, which tells us that if f of x and g of x are both antiderivatives of little f of x, then there is a constant, which we generally denote using a capital C, such that g of x is equal to big F of x plus c. And my check here is not very good, because I'm going to show that every function in this form is also an antiderivative, but it doesn't show that there are none that are in other forms entirely. Unfortunately, you do have to take that on faith, but for the sake of time, let's just go ahead and do that. But if I differentiate g of x, and I differentiate f of x plus c, well, I know that g of x and f of x are both antiderivatives of little f of x. That means that when I differentiate big G of x, I had better end up with little f of x. And when I differentiate big F of x, I should end up with little f of x. And when I differentiate a constant, I get 0. So at the very least, I know that adding a constant does not change or move me away from the family of functions. Again, this check does not go at all into showing that there are no functions of other forms that are not also antiderivatives, but for the sake of time, let's just go with this. Let's just look at how to figure it out, because that's more interesting anyway. To denote an indefinite integral, we are going to use the same integral sign we used for definite integrals. The only difference is we are going to leave off the limits of integration. And here's one we looked at before, the integral of 2x dx. We saw previously, just thinking about basic differentiation rules, this is the result of differentiating x squared. But it might also be the result of differentiating x squared minus 5, or x squared plus 7, or x squared minus 2 pi. So in general, we put a constant of integration at the end. I'm not sure if I gave that name before. We're going to call the capital C that shows up here a constant of integration. I guarantee that many of you, probably as many as half of you, are going to forget to add plus c whenever you perform an indefinite integral. I'm going to be perfectly honest with you. I tend to forget to add a plus c when I'm doing an indefinite integral. But it's important, it's vital that we include that plus c. If you continue onward in the study of calculus, you're going to end up in a branch of mathematics known as differential equations. And in differential equations, the goal is to use some sort of conditions, some sort of additional parameters on your integral to figure out which value of c is actually useful for the situation at hand. And so if I have that f of x is equal to the integral of 2x dx, and I have that f of 0 is 5 pi. Well, using what I just said, f of x must be x squared plus c. But if I take that and I plug it in to my condition, f of 0 is going to be 0 plus c. F of 0, I just said, is 5 pi. 0 plus c is just c. So now I know which particular constant of integration is useful. F of x is equal to x squared plus 5 pi. Right. This is another place where I implore you, learn from my own mistakes. When I was a student learning calculus, I didn't worry too much about including the plus c, and I got into the bad habit of leaving it off. I continued onward into the study of differential equations, which is the foundation of everything in physics and engineering. And I was in this bad habit of leaving off my plus c, and then I didn't have a constant to solve for when I plugged in the initial conditions, and very bad things happened to my work. Very bad things happened to my grade in that course. It was a bit of a nightmare. On the plus side, the resolution of that story is I took more differential equations. I kept taking it until I figured out that until I knew that I had figured out what to do, and that I actually had some semblance of knowledge on that. And now differential equations is my specialization. It's the thing that I spend all of my time thinking about when I'm not thinking about teaching, because, I'm a mathematician, and those are the kinds of things that mathematicians do. In any event, let me get my head out of the way, and let's think through the rules we have for differentiation. We don't have a lot. We have the trig rules. And those trig rules can give us some fairly simple integration rules. The integral of cosine of x is going to be sine x plus c. The integral of sine x, well, here we have that minus that showed up, so we have to keep that, is going to be minus cosine x plus c. The other ones are a little bit weird. It feels like there's no way this will ever come up. Sorry about that. As I'm writing this out, I realized that I'm trying to write and talk at the same time, and I left the dx off of the integral, which is also kind of important. Anyway, the integral of secant squared x dx is tangent x, and the integral of secant x tangent x is secant x. For those of you who continue onward into Calc 2, we will come up with some better rules for that, but we're not going to quite get there yet. What other rules do we have for integration? Well, we have the power rule. And we can turn the power rule on its head and come up with the integral of x to the m dx. And I do use a different value for the exponent here. It makes it make a little bit more sense what's happening, because m is equal to n minus 1, which means that n itself must be equal to m plus 1. The integral of x to the m dx is 1 over m plus 1 times x to the m plus 1 plus c. And then the last rule I have for you that we're going to be working on right now is the first one we talked about when we talked about derivatives, that is linearity. The derivative of a times f of x plus b times g of x is equal to a times f prime of x plus b times g prime of x. Right, that's linearity. And once again, we can turn that one on its head. The integral of a times f of x plus b times g of x dx is a times big F of x plus b times big G of x plus our constant of integration, where big F and big G are any one antiderivative of f and any one antiderivative of g, respectively. We talked about some other rules for differentiation: the product rule, the quotient rule, and the power rule. The product rule, the quotient rule, and the chain rule. And we'll talk about the chain rule a little bit later on. We should have enough time this semester to get that far. The product rule and the quotient rule are a little bit nastier to convert into rules for integration, and so we're going to hold off on those. For those of you who continue onward to the second semester of calculus, you'll see those rules in more depth. Before I go on and look at an example, though, I want to scroll back up and look at the power rule, because there actually is a bit of a problem here. If m is -1, the power rule fails, because you'll have 1 over 0. And 1 over 0 is undefined. It's an infinite value. And that's problematic. Once again, continuing onward to the second semester of calculus, you'll learn how to address that problem. But for right now, we're just going to assume that we can avoid the issue whenever we can. All right. So with these rules in hand, let's take a look at a couple of quick examples. The indefinite integral of 2x squared plus 3x plus 5 dx. Well, I know that I can split this up. 2 times the integral of x squared dx plus 3 times the integral of x dx plus 5 times the integral of, well, just dx by itself. Just like with the derivative, once you've done a couple of these and you get used to the idea, you're almost certainly going to skip writing out this step. But for the first couple, I think it's worth taking the time to do it. Now we use the power rule. To get to x squared, m is 2, m plus 1 is 3. So we'll have 1/3 times x cubed. To get to x, that's x to the first power. So m is 1, m plus 1 is 2. 1/2 x squared. To get to, well, nothing at all. Implicitly, I'm going to think about this as being x to the 0 power. So m is 0, which means that m plus 1 is 1. And using the power rule, this is 1/1 times x to the first. And then we need an arbitrary constant of integration. Before I get to the last step, cleaning this up, I just did 3 integrals, and I only wrote down 1 arbitrary constant of integration. A lot of students get hung up here and think, well, there should be 2 or 3 or more arbitrary constants. It's a matter of clarity and convenience, and also a little bit of laziness, that we only include 1. If you can take a function and add an arbitrary number to it, and then add another arbitrary number to it, and then add one more arbitrary number to it, you could have just stopped, thought about what would happen if you add those 3 arbitrary numbers together, and then add them all to the function in one go. It would have saved you a lot of time and headache, instead of writing it out in 3 separate steps. And so that's what we're doing here. There are 3 arbitrary constants that we're adding together. Because we can pick each of them to be whatever we want them to be, we can equivalently pick the sum of the 3 of them to be whatever we want it to be, and include just that as our arbitrary constant of integration, and that way we only need 1 in the expression. I do need to take a little bit of time and clean up otherwise. 2 times 1/3 is 2/3. 3 times 1/2 is 3/2. 5 times 1/1 is just 5. X to the first is just x. And the result here is 2/3 x cubed plus 3/2 x squared plus 5x plus c. And there is our indefinite integral of 2x squared plus 3x plus 5. I'll leave you with one to try on your own. I have here the integral, the indefinite integral of 5 times the sine of x minus 3 times the cosine of x dx. Right, so using the trig rules instead of using the power rule, but the same basic ideas hold. Take a couple of minutes, see what you can do with this one, and I'll see you in the next video.